Hi techies, have you ever walked into a McDonald's and found yourself in a long queue before you could even start ordering? That was probably the case back in 1940, but at least in 2024, we know there's a way to make things more effective. They have multiple queues and even machines to handle your orders promptly. We call it parallel processing. Do you know that's so similar to how it works in the world of computing? It may not sound as exciting as quantum computing today, but that's the secret behind why high-performance computing HPC clusters can process information millions times faster than standard desktop or server computers. But what exactly is HPC? How is it related to AI supercomputers? And importantly, how do those AI supercomputers train and run large language models or even multimodal AI models, including the famous GPT-4 and the new superstar GPT-4o, which power ChatGPT and BingChat? You'll find the answer to all those questions if you stick to the end of this video. You see, a standard computing system primarily solves problems using serial computing. It divides the workload into a sequence of tasks and then runs them one after the other on the same processor. The system described doesn't appear very efficient, does it? It's like lining up tasks and waiting for them to be processed, almost like the early days at McDonald's. But back in 1964, someone came up with a groundbreaking idea. Instead of using just one computer, they used a group of computers working together, aka computer cluster, kind of like a team with a bunch of members. This innovative approach greatly boosted the computational performance. Basically, how fast can a computer complete a complex calculation to the next level? Well, at least as expected by a regular functioning human being back then. High-performance computing, or HPC, is a technology, a practice, art and science that uses clusters of powerful processors working together to process data across multiple servers in parallel to perform complex computational tasks at exceptionally high speed. Then, how much faster is that? Let's put it into perspective. A laptop or desktop with a 3 Hz processor can perform around 3 billion calculations per second. Well, that is much faster than any human can achieve, but it pales compared to HPC solutions that can perform quadrillions of calculations per second, which is about 333, honestly I don't know how many threes anymore, times faster than a laptop or a desktop, and 120 times faster than a human. I guess HPC sounds cool, but what problems can HPC resolve? Just imagine all the use cases that require complex calculations combined with the power of parallel processing. These fall into the realm of HPC, which translate to human language, including complex tasks like DNA sequencing, automating stock trading, and running AI algorithms for tasks like autonomous driving vehicles. If we zoom out a bit, those use cases cover industries such as healthcare, energy, climate, smart cities, life science, edge computing, and many more areas. You know, in many ways, HPC goes beyond running multiple servers for parallel processing and performing complex calculations. It's more like an art and science of decoding the mystery of the world around us. Well, we have our theory, and things may change because of quantum computing. Well, I mean, maybe one day, not crazy. But if you're curious about our theory too, check out this video. Is HPC equal to AI supercomputers? At first impression, they are closely related, sometimes interchangeable. They all rely on powerful processors, GPUs, and high-speed interconnects. However, AI supercomputers specialize in AI workloads and are optimized for the next level. Right, that's what we'll get at. When it comes to large AI model training, AI supercomputers sound like an even bigger deal. AI supercomputers are one of the most advanced HPC systems available. So, what exactly does HPC bring to the table in this process? Large AI models can be trained on massive datasets using HPC clusters, making AI model training and inferencing much faster. You see, AI model training is about refining algorithms and adjusting parameters to improve their accuracy. This process involves feeding a large amount of curated data into selected algorithms. This enables the system to refine itself, generating precise responses. AI model inference, on the other hand, is about applying those trained models to make predictions or decisions in real time. Training jobs can consume vast amounts of computational resources, including CPUs, GPUs, or even specialized hardware like TPUs. This is why AI model training is largely driven by the emergence of GPUs and cloud-scale infrastructure, which require improvements in both specialized software and hardware. AI supercomputers can train models with hundreds of billions of parameters, as seen in the training and the inference of large language models, such as OpenAI's GPT models. For instance, the original GPT-3 had 175 billion parameters, which took thousands of GPUs running in parallel and weeks to train on some AI supercomputers built by Microsoft and OpenAI. The new generation, though, such as GPT-4, is even larger. It's based on 8 models with 220 billion parameters each, totaling about 1.76 trillion parameters, connected by a mixture of experts, MOE, which is a machine learning technique in which multiple expert networks are used to divide a problem space into homogeneous regions. The technique to train those models is called data parallelism, training many instances of the model at the same time on small batches of data. After each batch is processed, the GPUs exchange information and then process to the next batch. That's why you require training infrastructure at large scale. Those large AI models leverage self-supervised learning, where they learn by examining billions of pages of information over and over again. They're super resource intensive and can quickly become expensive. Well, when I say expensive, it can mean time and money. So, how long did it take to train the GPT-3 model? OpenAI released GPT-3 in June 2020. Typically, training GPT-3 on a single NVIDIA Tesla V100 GPU instance would take an astonishing 355 years and would cost around $4.6 million. However, Microsoft built a super powerful supercomputer in its Azure data center, equipped with over 285,000 CPU cores, 10,000 GPU cores, and high-speed network connections for each GPU server. The supercomputer, coupled with innovative software technologies like DeepSpeed and ONNX runtime, enables deep learning distributed training and inferencing. It allows OpenAI to use advanced techniques like data parallelism to overcome memory limitations by dividing the training data into smaller batches, allowing them to be processed in parallel across multiple GPUs. So GPT-3, with its 175 billion parameters trained on 300 billion tokens, theoretically could have been trained in just 34 days using 1024 A100 GPUs. But wait, there's more to the story. GPT-4 launched in March 2023, levels up again with multimodality. This upgrade lets GPT-4 handle both images and text inputs, along with better reasoning skills and a deeper understanding of user prompts. GPT-4 was trained using around 25,000 NVIDIA A100 GPUs for about 100 days, taking about 6 months to develop. The challenges for AI supercomputers go beyond just making them faster without sacrificing performance. On the hardware side, you need really high bandwidth networking, such as infinity band, with high throughput but minimal latency, power consumption, and heat dissipation, which are also on the table. On the software side, you need frameworks such as DeepSpeed, which is developed by Microsoft Research for large-scale deep learning training and inferencing efficiently and effectively. Things may look perfect on the footprint, but what's really important in real life is handling failures that occur when running intensive workloads on a regular basis at such a large scale, such as servers or network connections going down. It's important to reduce the frequency of those failures, and when they do happen, quickly figure out what went wrong and fix it. But you know what? Today, we have the technology to tackle this challenge. When the training goes wrong, the multiple GPUs required to train LLMs don't operate on the same board or even the same rack in the data center. That spread out to manage power consumption and heat effectively. This setup ensures scalability, enabling networks and clusters to expand to thousands of units as demands grow. You may ask, so why would we even care about this anyway? In reality, training large AI models could take days, weeks, or even months. What if something goes wrong in the middle of a process? That's why it's crucial to periodically save the state of the AI model in an incremental fashion. If anything fails, it can quickly resume the recent changes instead of starting from scratch by creating a checkpoint. This is where Project Forge from Microsoft comes in. This technology, combined with a global GPU scheduler, allows you to pause a job and seamlessly migrate to a different cloud region with minimal impact on progress. The same technology is also used for load balancing those jobs on a global scale, as these jobs are assigned to virtual clusters that map the physical resources in a data center, ensuring continuous training and inference jobs without interruption. This is why we enjoy using BingChat, GitHub Copilot, and ChatGPT, but there are so many things going on behind the scenes. This reminds me of how NVIDIA built its AI infrastructure using cloud-native technologies, such as Kubernetes, as an abstraction layer. This not only helps maximizing resource efficiency, but also ensures scalability and availability. So if you're interested, you can find out more in this video. AI infrastructure is the backbone of large AI models, and that's how we can do so many fascinating things and build cool products with them. If you found this video helpful, then why not stay with us for more? I'm making videos like this one on a weekly basis, so you'll know what to do. I'll see you in the next one.